This is the Tomahawk, a subsonic cruise missile with high precision and long range, suitable for all climates and temperatures. Jet engine powered, like those in airplanes. It can be launched from underwater, from submarines, or from surface ships like destroyers. He is a top pride of the American Navy. That's because after being launched, the Tomahawk can fly for more than 2,500 kilometers. Yes, more than 2,500 kilometers. It has a data link that lets it switch targets mid-flight. In addition, when it reaches the target, the missile can be put into standby mode, with the missile flying over the target for hours while waiting for the ideal moment to then strike it. And on top of all that, it can fly extremely low, about 15 meters above the ground, avoiding detection by radar systems. It features an advanced digital system that helps it navigate natural obstacles like mountains and elevations, and avoid obstacles such as buildings, houses, and trees. He is Raytheon's pride, his current manufacturer. Tomahawks originated in the 70s through a partnership between McDonnell Douglas and Maryland's Applied Physics Laboratory. The idea was to create a cruise missile that would fly at subsonic speeds, that is, at speeds below the speed of sound, but the missile had to fly at very low altitudes to avoid detection by enemy radars. The missile was designed to carry 450 kilograms of explosives or W-80 nuclear warhead with destructive power from 5 to 200 kilotons, or just over 13 times the Hiroshima bomb. One of the main features and key differences of the missile would be its flight at very low altitudes, around 15 meters. At these altitudes, buildings and other structures usually block radar waves, thus giving the missile a huge advantage and an almost undetectable flight. A modern Tomahawk is 6.2 meters long with the booster, 52 centimeters in diameter, a 2.67 meter wingspan, and weighs 1,300 kilograms or 1,600 kilograms with the booster. And it can reach a maximum cruising speed of 930 kilometers per hour. Tomahawks are typically launched vertically from special pressurized compartments on the decks of destroyers. In the initial launch phase, the Tomahawk is propelled by an extremely powerful rocket motor powered by solid fuel, which operates for about 10 seconds and propels the missile from the compartment where it is launched to several kilometers away. Then, this motor is ejected and the Williams International F-107WR-402, a turbofan jet engine, takes over to propel the missile and carry it to its target, which can be more than 2,500 kilometers away. This engine uses a fuel called TH dimmer, which is also one of the components of the fuel used in aviation, jet propellant. 9. When the missile is launched, both the central wings and the rear fins are retracted, so the missile is more compact and takes up less space inside the launch tube. A few seconds after launch, the wings are extended and begin to generate lift for the missile's flight. The initial propulsion phase uses a solid fuel rocket engine for several reasons. The first reason is that these engines are very powerful, and that power is especially necessary during the initial launch phase, when the missile is vertical and much heavier because it hasn't started consuming the fuel inside its tanks yet. Another reason is that solid fuels can be stored for years, allowing missiles to remain fully ready without last-minute fueling. Another reason is the missile quickly reaches high speeds, offering two key advantages. First, the missile will hit the target much faster. Second, high airflow helps ignite the jet engine more easily. Tomahawk features a cylindrical design and contains an imaging infrared seeker inside, and at the back, guiding devices such as inertial navigation systems, global positioning system, terrain contour matching, time of arrival, and digital scene matching area correlator. We'll soon understand what all these things are. Further back, there's the data link, a device that maintains constant two-way satellite communication between the missile and the command center, which sends instructions like trajectories, target changes, among others. Behind the data link is the missile's explosive payload, which may be conventional or, in early models, nuclear. In the center, there's a tank containing the fuel that will be used to propel the missile during flight, and on the outside, wings to generate lift. At the rear and underneath, there's a retractable air intake that supplies air to the missile's engine. The engine is angled downward to enhance air intake. At the rear, an exhaust duct expels engine gases and fins provide flight stability. It's also at the rear where the solid fuel booster is attached for the initial launch phase. Now that we know the basics about the missile, comes the most interesting part, how the Tomahawk flies and finds its target, and how it knows this is the right target. It all starts before launch with the Tactical Tomahawk Weapons Control System, or Tactical Tomahawk Weapons Control System, an integrated system with navigation, communication, situational awareness, and vessel launch systems. It calculates the missile's trajectory to the target. Previously, many missiles used inertial systems and global positioning system for guidance. However, with only these systems, missile accuracy was about 10 to 20 meters. In other words, the missile could miss the exact target point by just over 10 meters. To solve these issues and boost accuracy, Tomahawk's advanced navigation and guidance systems use technologies like terrain contour matching, time of arrival, and digital scene matching area correlator, First, the missile uses terrain contour matching or terrain contour matching. This technique uses terrain elevation differences. First, the terrain the missile travels through is split into sectors. The elevation differences between sectors are used to create a digital map which is loaded into the missile's computers. This data typically comes from satellite mapping. During flight, the missile uses a radio altimeter to measure elevation differences and compares them with stored data. This way, the missile knows if it is flying on the correct trajectory, and if necessary, it makes corrections to its course to stay on the right path. However, this technique fails when the missile flies over the sea or deserts where height rarely varies. In the past, many Tomahawks would avoid areas with little variation in terrain height and would take another route to the target. However, this made all the missiles follow the same path, making them easy targets. That's what happened in the Gulf War. To address these issues, the Digital Scene Matching Area Correlator, was added alongside Global Positioning System. This technique uses a camera to photograph terrain and compare it with images stored in the missile. This technique ignores terrain height variations. It also boosts the missile's accuracy as the system can recognize buildings and houses. Only photos of the target and its surroundings are inserted into the missile system. Since it's very difficult to insert photos of the entire route the missile will travel. However, weather, rain, snow, and other conditions can cause major differences between the missile's stored photos and those it takes in real time. That's why, in the most recent versions, the Tomahawks are equipped with the Imaging Infrared Seeker, a type of seeker that scans the terrain as the missile flies and allows it to recognize and find the target, regardless of whether it's day-night or the weather conditions, since the camera will use infrared. This also allows checking whether the target was hit or not, since the data is sent to the ship's control center. With all these systems, the accuracy of Tomahawk missiles has increased a lot, and historically, the accuracy rate is around 5 meters. In other words, it can miss the exact target point by up to 5 meters, allowing it to fly extremely low in inhabited areas or in highly protected zones. As it approaches the target, the missile drops to an altitude of 30 meters or less before impact. And speaking of impact, Tomahawks don't need a direct hit on the target for their explosive charge to detonate. It's enough to get close enough or reach a pre-established level for their preset charge to be detonated. Subsonic is a feature, not a flaw. In a world where the trend points to supersonic and hypersonic missiles as being more effective, the Tomahawk follows a completely opposite path. Because it is subsonic and flies at relatively low speeds compared to other missiles, Tomahawks can fly with greater fuel efficiency. That's why they can fly long distances of more than 2,500 kilometers. This also allows them to be much more maneuverable compared to supersonic and hypersonic missiles. In addition, the ability to take a non-linear route to the target sets them apart from other missiles. There's the Navy version, launched underwater from submarines. A high-pressure air system ejects the missile several meters above the water. Then, its solid fuel engine immediately kicks in, propelling the missile in this first stage. Afterwards, it is ejected and the jet engine starts operating. How missiles are launched underwater is a topic for another video. On top of all that, it's cheap, costing around $1.5 million per missile. Raytheon, maker of Tomahawks, also produces the Standard Missile 6, which reaches Mach 3.5 times the speed of sound, but has a much shorter range and costs up to 4 times more. Tomahawks last 30 years, but after 15 inactive years, they're evaluated, recertified, and put back into use. Since its 1983 debut, around 8 Tomahawk variants have been made, including the BGM-109A with a W-80 nuclear warhead, which was retired in 2013. The RGM is Universal Guided Missile. 109B was an anti-ship version, while the ground-launched BGM-109G carried a W-84 nuclear warhead, but it was retired from service in 1991. But Block 4 is the dominant variant and is currently fully operational in the United States arsenal. This version lets the missile get data from planes, drones, satellites, soldiers, armored vehicles, and ships to locate its target. It also lets the missile's course be changed in flight to any of 15 preset targets or redirected to a new one. In this version, the missile can enter standby mode, circle the target at a safe distance until commanded to attack, or fly to a preset area to self-destruct if the attack is cancelled. The missile also transmits its status, real-time battle images, and other data to the command center via a direct two-way satellite link. But this version will gradually be replaced by the Block 5 version, which entered service in 2021 and includes many more improvements and sophisticated features.